name's Josh Wieder. I've been an enterprise sysadmin since about 2007 when I was hired at a carrier-neutral data center in Florida, where I still live today, but please don't hold that against me. I worn a lot of different hats in that time, usually involving Linux and MySQL, more recently with AWS. Today, I'm here to talk to you a little bit about how the company I work for, Buyer's Edge Platform, implemented Teleport. Before I do that, though, I wanted to thank Teleport for inviting me here, giving me an opportunity to spend today with all of you guys instead of Hurricane Nicole. I hope that earns me a little bit of sympathy if I say anything stupid today. So back to Teleport, my employer, Buyer's Edge Platform, grew very quickly following the pandemic. That meant we had to onboard new team members at a rate we never really had to in the past. It increasingly became a burden to our tech support team. We're a technology company. We employ hundreds of developers, data scientists, people with vastly different roles. A lot of those onboards come from acquisitions in addition to hiring, so I might have a completely siloed environment for a lot of these users. We've got each dev needing access to a slew of different resources, Active Directory, Linux shell accounts, databases, custom applications, Kubernetes, VPNs. Even with systems like LDAP in place to help us manage this, onboarding new team members could take hours and involve multiple staff. Developing a solution to this problem in-house just wasn't practical for us. We had other projects to work on. But Teleport stood out as being more feature-rich and well-documented than some of the other competing products that we looked at to solve that for us. Teleport's feature-rich, and there's a lot of ground to cover. Because we're starting a little bit late today, I'm just going to kind of breeze through this as quick as we can. Let's go ahead and get started. When you deploy Teleport's HA autoscale cluster Terraform example for AWS, you end up with something that looks like what you can see on the slide. We needed to figure out how to fit all that into our existing infrastructure. All of our new infrastructure is deployed as code using a CI/CD pipeline and GitHub Actions. We ultimately decided to run Teleport cluster services like the last colleague from DoorDash in a series of EC2 instances instead of in a Kubernetes cluster. It was just the best fit for our circumstances at the time. But if you do plan to deploy in EKS or Kubernetes, you'll have a very different deployment experience than what I'm going to describe here. We also needed Teleport to live in our AWS environment. And that environment exists as a multi-account AWS organization using Control Tower. Teleport needed to be deployed within its own AWS account for our environment. That would mean that our Teleport cluster would need to connect to resources outside of its own VPC. There are many different ways to address this. DoorDash talked about a transit gateway. Another way is to use AWS VPC peering to connect subnets from other accounts to the private network for Teleport. In that case, you would assign the network load balancer assigned to authentication services in your etc Teleport YAML file like this. There's another option here, though. This might not be feasible in all scenarios, and the colleague from DoorDash in the last talk talked about how exposing an authentication, your auth instance in this way is not preferable. So fortunately, there's another option. So one thing that we ended up going for was using Teleport's dynamic database registration service. Managing resources across VPCs wasn't our only concern. We didn't want to manually manage config information for our many dozens of databases. A significant amount of overhead would be involved with manually configuring those databases, adding them into Teleport, changing the config when the databases change. Fortunately, the bulk of our DBs right now are in RDS, which allowed us to take advantage of Teleport's auto discovery feature. It's pretty well documented on the Teleport website. So what do you do if your databases are hosted within a separate AWS account? The normal configuration of this type of AWS account design will result in either authentication failure to the database or one of another series of problems. The approach we used was to deploy a small proxy instance inside each AWS account that hosted databases. Teleport installed and configured using the joint key role DB to create a DB service proxy, and using IoT node tunneling to connect clients using the public-facing proxy address. Etsy teleport YAML file for these proxies should look something like this. Another reason for adopting this methodology is that, at least when I was building our initial cluster, the proxy service and DB service for teleport were unable to run on the same EC2 instance. Similarly, provision services like kube service don't have that limitation though. It's not necessary to enable multiplexing in teleport in order for this to work. There are other ways to connect databases from one AWS account to resources in another one. For example, using an RDS proxy. It's also possible to combine static and dynamic registrations. For example, if an AWS account contains a combination of self-hosted databases and RDS, you can use auto detection for RDS by using static configurations for the self-hosted databases. Just add a different block. You'll need to complete the other steps for self-hosted DB registration, like setting up TLS on the database server. Make sure that the URI of the server is valid for the SSL certificate you created during the static DB registration process. So integrating teleport into our CI/CD pipeline is an ongoing process for us. We use GitHub Actions and Atlantis, and the Terraform that teleport provides works well in our environment. One of the most exciting new features from teleport is their Terraform provider, though. This allows you to manage teleport users, roles, and auth connector settings from within Terraform. There's a couple of quick hints for keeping things organized. Consider creating several different Git repositories for your teleport project. One thing I like to do is create a primary repo for our cluster. Has things like infrastructure files, Terraform, stuff like that. Second repo for Terraform with users, roles, and connectors. And then a tertiary repo for AMIs. The default Terraform makes no accommodation for a shared state. So hopefully you'll have some help working on your Terraform from time to time. But before you provision the teleport Terraform, create an S3 bucket to store your shared state and DynamoDB table to handle the locks. This can be a little confusing because there is a default DynamoDB table created for locks in this Terraform, but those aren't the locks that you're looking for. Don't forget to encrypt your S3 bucket either. So while we're on the topic of protecting secrets, the default teleport cluster Terraform prompts you to provide 2 secrets in plain text: an admin password for Grafana and your teleport enterprise license key. The teleport Terraform takes these plain text values from and uploads them as encrypted secure strings to AWS SSN parameter store. This helps get things going quickly for a dev environment, but is not acceptable for production. We use ACM for our certificate manager. Saved us a lot of time. Quite a bit of Teleport's extra scripts deal with creating and managing Let's Encrypt certificates on the instances that are running Teleport. There's nothing wrong with using Let's Encrypt, but ACM is inexpensive, it's stable, and it made sense for us to offload this task. If you'd like to do that, just enable Use ACM in your Terraform. You can also import certificates into ACM to use for this, but make sure you only use ACM-generated certificates. If you have a need to use a non-Amazon issued certificate, the Terraform functionality included probably won't work. So one of the things that isn't really well documented is how Teleport uses deployment scripts within EC2. So if you build a new instance using Teleport's AMI, and go into the user local bin directory, you'll see scripts like these, and I won't list them all there for you. There are quite a few of them. If you were Many of these, as I just mentioned, handle the Let's Encrypt encryption process. Understanding the basic functionality of these scripts is extremely helpful when troubleshooting deployment issues. 9 times out of 10, when a teleport instance fails to provision properly, it's some sort of conflict between these files and your intended configuration. Most of my troubles come from a script named teleport generate config, the script that converts the values provided in Terraform into the teleport systemd service, and the etc teleport YAML config file that will be responsible for the configuration of teleport. The current version of Terraform, or of the Terraform example, provides easy means for enabling MySQL, Postgres, and MongoDB listeners. But the fact is, if you plan to use Kubernetes or a less common DB platform like Redshift or Snowflake, or if you need to use SSO, you'll either need to modify these provisioning scripts directly or manually edit etc teleport YAML after provisioning. You may find that manually editing etc teleport after provisioning or managing the nodes provisioned by Terraform outside of Terraform can be perilous. The default auto-scaling group policies will terminate instances when they reboot, for example. I don't recommend taking this course of action, but there are times when it's necessary. For example, you might enable termination protection on at least one auth and proxy instance, and add a line like the one on this slide to your proxy ACM file. Something else to keep in mind is that modifications to your launch configuration can pretty easily result in AWS destroying all of your EC2 instances. Even if Terraform creates the replacement instances before this happens, there's a good chance you're going to have some downtime as a result. So what I like to do is start by reducing my cluster down to a single auth instance and proxy instance. When upgrading teleport, I then go ahead and upgrade the cluster per the published instructions by installing the new binary. I then create a second launch config, associated auto-scaling group, and a secondary teleport AMI name variable that points to the upgraded version. Don't forget to add a secondary AWS AMI block. By doing this, you can eliminate the risk of downtime when removing the old instances too quickly or from mistakes in the new configuration. Instead, you can bring the new servers online at your convenience, then remove the old versions of the launch config and ASG from Terraform when you're ready to replace them. So I was going to go on a little bit here about rolling your own AMIs, but because we lost a bit of time here messing around with my laptop, maybe we'll just open it up for a few minutes of questions if anybody has some. It's okay if no questions or two. Sure.
Yeah. So, real quick question. Is that on? I don't know. Okay, there we go. This is one region, right? So when you're talking about deploying all of this is like multiple AZs, one AWS region. Have you looked into how you might do the same thing and having teleport work in multiple regions so that you have some redundancy there?
That's something on, that we've been planning for in our next year operations. I mentioned a little bit about how we're integrating some of the new Terraform functionality in our CI/CD pipeline. One of our acquisitions brought in a large Azure environment, and so multi-cloud is something that we're looking into. That may ultimately be the direction that we look into as opposed to duplicating across an AWS region. And Terraform will probably be a big part of that. It's like a cool standby maybe in a just completely separate provider.
Anyone else? Questions for Josh? No? Great. Thank you so much, Josh. This was great.